Okay, in this video we're going to do questions 57 to 59 in the June 2013 Chemistry Regents exam. Alright, so we have a heating curve here for this set of questions, and it says this is a sample of water, and it tells us the starting temperature, which we can also tell from the graph, and then the finishing temperature, which we can also tell from the graph. So a couple of things here that are important to note. We're at standard pressure here, so we can tell actually based on the boiling and melting point of water here that standard pressure is what we're at, and then also that the units on our axes here, we have temperature and heat on the x-axis. So this is really just a standard heating curve. Okay, so 57 asks us what happens to the potential energy and the kinetic energy of the molecules during the interval AB. Alright, so AB is this first interval, at the beginning here. So during this interval, we are increasing our temperature. All right, so we can tell that from A to B, right, we started at negative 25 degrees Celsius and ended up at 0 degrees Celsius. So because we're increasing our temperature here, we know that the average kinetic energy of the particles is going to be increasing, because that's what defines temperature, right, is the average kinetic energy of the particles in a substance. So because we are increasing the temperature, we must be increasing the kinetic energy of the particles. So as part of your answer here, you would say the kinetic energy of the particles is increasing. So then what about the potential energy as well, because it asks us to answer about both of these different types of energy here. So the potential energy for section AB, the potential energy is actually going to stay the same because we are in the same phase here, right? So remember on these heating curve diagrams, we have a single phase here. In this case, it would be solid as the temperature is increasing, and then BC here, these plateaus, this would represent a phase change. And from C to D, again, this would be the same phase. This would now be in the liquid phase. And then D to E would also be a phase change as well. This would be the phase change of liquid to gas. And then from E to F, again, this is all the gas phase, right? So we're increasing the temperature there in a single phase. So for section AB, this is all in the solid phase. All we're doing is increasing the temperature of these particles. So we are increasing the kinetic energy of the particles, but the potential energy is staying the same because it's in the same phase. If we were changing our phase, let's say changing from solid to liquid, that's going to result in an increase in potential energy because we've taken those intermolecular forces and broken them and spread those molecules, or well, in this case molecules, apart. That's going to be a change in potential energy. But if we're in the same phase as we are for segment AB here, the only thing that's changing is the kinetic energy because we're increasing the temperature. So the answer here would be KE should increase and the PE should stay constant. Alright, so the kinetic energy increases here because we're increasing the temperature, and the potential energy remains constant because we're staying in the same phase. Okay, so for question 58, what is the total amount of heat added during interval CD? So heat added is on the x-axis here. So if we look at this at C, we could estimate here maybe we're starting at about 7 kilojoules, because if we're going up on a scale here by 4s for each box, this looks almost all the way to the box there. We could call that 7 kilojoules. And then over here we have maybe about 15 kilojoules here, because again we have 12 here, this would be 16, so we're maybe at about 15 kilojoules there. So the amount of heat added during interval CD would just be the difference between these, so 15 minus 7 would give us 8 kilojoules of heat added for segment CD there. Alright, and the last question here, 59, says explain why the heat added during DE, so why this amount of heat added is greater than the heat added during section BC. Alright, so why is this greater than this amount of heat added? So if we look at this, we think what is happening during segment DE, and we said before we're going from the liquid phase to the gas phase. And during segment BC here, we're going from the solid phase to the liquid phase. So why is this line so much longer from DE? Why are we adding so much more heat to go from the liquid to gas phase than we did going from the solid to liquid phase? So to answer this, you really just need to look at your reference tables, table B down here at the bottom of the reference tables, and, at the middle of the front page of your reference table. So if we look at the heat of fusion, fusion is the melting process. This is going from solid to liquid. The heat of fusion, the amount of heat we need to add to do that is 334 joules per gram. But then the heat of vaporization, which is going from liquid to gas phase, this is a much greater heat required than for the heat of fusion. So the heat of vaporization is higher than the heat of fusion, which means it takes more energy to boil a certain amount of water than it does to melt it. All right, so this question 59, it's purely based on the heat of vaporization and the heat of fusion for water. So for water, because the heat of vaporization is so much higher, it's going to require a lot more energy to vaporize or boil this water than it is to melt the water from solid to liquid, because the heat of vaporization for water is much higher than the heat of fusion. So that's what you would say for 59. All right, so we'll come back in the next video with question 60. Thanks for watching.